Bismillahirrahmanirrahim. So, chapter 2, groups. Previously, we have talked about chapter 1, introduction to groups. And in that, we have described some of the things about groups, and then how we had uh, how we used the symmetries of a square to actually talk about the properties we need to check for a group. Then we have presented the Cayley table, and then we have said uh, that from this Cayley table and the properties of the symmetries of the square, how we get the closure property, identity element, and inverse element for each one of those, and then associativity. Then we have particularly talked about the hydral groups, like where they lie and where can we find them in nature and in art. So these are a few examples where we can find them. Now we will talk about the chapter 2 groups itself. Before that, I have presented some quotes. You can pause the video and then check those quotes. There is one more I'm going to write, and that would be that he, where we are talking about the great Norwegian mathematician Abel, has left mathematicians something to keep them busy for 500 years. So, and this was said by Charles Hermite. So, if we particularly talk about Abel, Niels Abel, he was born on August 5, 1802, in Norway. And at the age of 16, he began reading the classical mathematical works of Newton, Euler, Lagrange, and Gauss. And when he was 18 years old, his father died, and the burden of supporting the family fell upon him. So he took in private pupils and did odd jobs while continuing to do mathematical research. At the age of 19, Abel solved a problem that had vexed leading mathematicians for hundreds of years, and that was he proved that, unlike the situation for equations of degree 4 or less, there is no finite closed formula for the solution of a general fifth degree equation. And this was first proved by him, and then later on we know whatever we know about it. And he died around 1829, and he was 26. And his solutions to quantic problem laid the groundwork for many of these subjects. So, and in the recognition of the fact that there is no Nobel Prize for mathematics, in 2002, Norway established the Abel Prize as the Nobel Prize in mathematics. Okay, perfect. So, Niels Abel, remember the name. Groups. We'll talk about the definitions and examples of groups. So, let's start. If we talk about particularly the term group, was used by Berlioz, pardon my spelling mistakes, I do all the time, around 1830, to describe sets of one-to-one functions on finite states. That could be grouped together to form a set closed, closed under composition. And if you look at the definition of a group from the perspective of the higher education student, you will agree with this thing. How, as is the case with most fundamental concepts in mathematics, the modern definition of a group that follows is the result of a long evolutionary process. It was not given in the first place, it was given later. And the modern definition, which we use now, was given by both Heinrich Weber and Walter von Dijk in 1882, and it did not got acceptance until the 20th century. We'll stop. Now, we might know about the definition of the binary operation, but eventually I'm going to present it. Binary operation. So let's take set G a binary operation on G is a function let's say defined with star from G to G that assigns each ordered pair of elements of G and element of G. So by this we mean that if you apply this star on AB, let's say in the vague definition, this will give something like this, and this will lie inside G. So this is the binary operation, and this binary having a binary operation on G is called the having the closure property. So this is closure. Okay. Now the most familiar binary operations are ordinary addition, subtraction, multiplication of integers. Okay. Now division of integers is not a binary operation on the integers because an integer divided by an integer need not to be an integer. It's not closure. So if something is not closure, that will not be considered as a binary operation. The binary operations addition modulo n and multiplication modulo n on the set. So in an example, we can say the binary operation addition modulo n addition modulo n and multiplication modulo n on the set is 0, 1, 2 up to n minus 1, which we denote by this n, or simply Zn, plays extremely important role in abstract algebra. In certain situations, we will want to combine the elements of Zn by addition modulo n only. In other situations, we will want to use both addition modulo n and multiplication modulo n to combine the elements. Okay, it depends on the situation we are working on. It will be clear from the context whether we are using addition only or addition and multiplication. For example, when multiplying matrices with entries coming from Zn, we will need both addition modulo n and multiplication modulo n. Okay. Now we are able to present the actual definition of groups of a group. So let's define that. Let's define what is a group in abstract way. So let's say let G be a set together with a binary operation. We usually take it multiplication, but it can be addition. So G to G that assigns sends A comma B to AB, and this AB will also lie inside G as A comma B for all A comma B coming from G. We say G is a group. We say G is a group. Under this operation, if the following three properties are satisfied. Number one property is we should have associativity. Remember, we like we also add the closure property as a property, but when you have this binary operation, you are actually asking for the closure as. So you don't have to define it again. Associativity. That means that the operation should be associative, and that could be proved by. Remember, this is not order pair. This is just a multiplication of AB into C and A into BC for all A, B, C coming from G. Number two is we should have identity in the group. And that is to say that we should have an element E, let's say A, E should be E, A, and again A for all A in G. I can say there is an element E in G such that we have this property. And number three could be, number three would be that we should have inverses for each element. So for each element A in E, A in G, there is an element B in G called the inverse of A such that AB is equals to BA is equals to E. Right? Now this is how we define the group. This is what we call a group. Okay. Now in other words, group is a set together with an associative operation such that there is an identity, every element has an inverse, and any pair of elements can be combined without going outside the set. That is having an inverse. Now be sure to verify closure when testing for a group because that means be sure to check whether the binary operation is well defined or not. Now, notice that if A is the inverse of B, then B would be the inverse of A, right? Okay. If a group has the property, so let's say here, if a group has the property that AB is equals to BA for every pair of elements And B, we say that the group is abelian, and abelian is named after Niels Abel. Group will be non-abelian if there is some pair of elements A and B for which it is not equals the AB is not equals to BA. Okay. Now that we have the formal definition of a group, our first job is to build a good stock of examples. These examples will be used throughout the text to illustrate the theorems. Okay. Now let's define the examples. What would be the simplest one? The simplest example could be, let's take the set of integers z. Now remember, the German word for numbers is Zahlen. That's why we denote integers with z. Let me write that for the reference. German word for numbers is Zahlen. Okay, the set of integers, the set of rationals, rational numbers, which we denote with q, and q is for quotients, and the set of real numbers, are all groups, are all groups. What is the operation? Under ordinary addition, which means what? Which means that the binary operation here is taking elements a comma b and producing a plus b for all a comma b are coming from z, q, r. Okay, and then you can carry on and check the associativity. And so what would be the associativity? A plus b plus c and a plus b plus c. This is 1, this is 2. 2 would be what? Identity. Okay, a plus 0, 0 plus a would be a. 3, inverse. So for each a there would be some minus a, and for each minus a there should be some a, and that will be given to 0. So 0 is identity. In this case, minus a for a is inverse. Right? Perfect. Number 2. Now, number 2 is Number two is the set of integers under multiplication or ordinary multiplication is not a group. And where it fails, since the number one is the identity, that we good. But number three fails. Property three fails. So property three fails. For example, there is no b such that 5b is 1. Or you can say there is no b such that some a into b is 1. So for a in integers, there is no b in integers such that ab is 1. Okay, right. Now example 3 would be the subset one minus one iota minus iota of complex numbers is a group under what? Under complex multiplication. Under complex multiplication. Note that minus 1 is its own inverse. Okay, whereas the inverse of iota is minus iota and vice versa. So minus 1 is its own inverse and inverse of iota is minus iota and vice versa. Right? Perfect. Example 4. We need a lot of examples because we are going to use them for understanding of many things. The set Q plus the positive rational numbers of positive rationals is a group under ordinary addition and ordinary multiplication also. Ordinary multiplication is the inverse of any a in q plus is 1 over a, which is a power minus 1. Perfect. Right. Number 5, Now, we have some strange thing happening here, which is, let's say the set S of positive irrational numbers together with 1 under multiplication satisfies the theory properties given in the definition of a group, but is not a group. And that's very strange, isn't it? Because it does not satisfy the first thing, which should be that the binary operation is not well defined. Indeed, indeed, product of under root 2 with under root 2 is 2. So S is not closed under multiplication. Right. Number 6. Number 6 says, let's take a rectangle array of the form rectangular array of the form A, B, C, D is column 2 by 2 matrix. Now, the the set of all 2 cross 2 matrices with real entries and we denote that set by M2R. No need to give this definition, just this. M2R is a group. Is a group under component-wise addition. That is, the addition would be that we can add 2 matrices A1, B1, C1, D1. Let's say this is our first matrix, the second matrix, and we would do the addition of the matrices A1 plus A2, B1 plus B2, right? And the identity is a zero matrix, and the inverse of A, B, C, D is minus A, minus B, minus C, minus D. Okay, perfect. The last one could be, but we have more. So, example 7 says the set Zn we have talked before, which has 1, 0, and minus 1 for n greater than or equal to 1 is a group under addition modulo n for now let's say for any j inside Zn, the inverse of j is going to be n minus j. And this group is usually referred to the group of integers modulo n. Now, as we have seen, the real numbers, the 2 cross 2 matrices with real entries, and the integers modulo n are all groups under the appropriate addition. But what about multiplication? In each case, the existence of some elements that do not have the inverses prevents the set from being a group under the usual multiplication. However, we can form a group in each case by simply throwing out some elements from the set. Let's say in example number 8, the set of R star, which is of non-zero real numbers. There is no zero in them now. Numbers is a group. Is a group in the ordinary multiplication. The identity is 1. The identity is 1. The inverse of A is 1 over A. Okay, perfect. Now, some more important examples we can present. Let's say the famous example would be that let's take the 2 cross 2 matrices Now the determinant of a 2 cross 2 matrix is determinant of a 2 cross 2 matrix is going to be AD minus BC, right? Now if A is a 2 cross 2 matrix, determinant A denotes the determinant of A. So we say that determinant of A is the determinant of A, the set, then the set which we call GL2 over R would be a set which has 2 cross 2 matrices with the condition that these all A, B, C, D are coming from real numbers, with additional condition that the determinant AD minus BC is not zero. We call it general linear group. Then GL2R is a group under the component wise addition. Now, sorry, not the addition, but under the multiplication, under the matrix multiplication. That can be shown as that A1, B1, B1, B1 product with A2, B2, B2, D2 be equal to A1, A2 plus B1, C2, then A1, B2 plus B1, D2, and then again C1, A2 plus D1, C2, and then C1, B2 plus D1, D2. Okay, and then the first step in verifying that this is actually a group would be that show that product of two matrices with a non-zero determinant also has a non-zero determinant, and this follows from the fact that for any pair of 2 cross 2 matrices A and B, we have this property of determinants, that determinant of A, B is actually equals to determinant of A and determinant of B. Then associativity can be verified by direct but cumbersome calculations. The identity is the identity matrix 1 0 0 1. The inverses of any of a matrix A, B, C, T is actually can be written as D over, let's say this is A, A is equals to this, then this is going to be determinant of A, D over determinant of A minus B over determinant of A, and then minus C over determinant of A, and A over determinant of A. Explaining the requirement that determinant should not be zero, that determinant of A should not be zero. And another useful fact about determinants is that if the determinant of A inverse is actually a determinant of A and take its inverse. Okay. Now this very important non-abelian group. Remember, this is not an abelian group. This is called the general linear group of 2 cross 2 matrices over R. This non-abelian group is called the general linear group of 2 cross 2 matrices over R. Now, I think this is becoming a very long lecture. So I will end this here, and then we can talk about more examples in the next one. Thank you so much. Take care. Bye.